Hello everybody, welcome to the channel again. I appreciate you stopping by. Hey, if you see what and you like what I'm doing, go ahead and give me a thumbs up, subscribe to the channel. It all helps. I appreciate it. I appreciate all the support from everybody so far. Tonight I wanted to do another study video for the extra class. Go through the questions. I think it's going to finish up this current chapter we're on. So with that, let's stick around. Alright, I appreciate you sticking around. As anybody that's watched some of the videos or followed along with me, I try to do between 10 to 15 questions per video or live stream, just to keep it kind of short and brief and not stretch any of our attention spans, to help with the retention too. And it's definitely helping me retain some of the information as I go along, so I appreciate all the support there. Let me get this switched over here to... Alright, as we can see here, we are still going through the current Gordon West 2020 to 2024 extra class element 4 book that he's got out. It's all the current questions for the actual in effect question pool, and we've gone through a bunch of chapters. As you can see so far, we're up to right here. Then current chapter is actually modulate your transmitters, and I think we're going to actually finish this chapter out tonight. It's about another 12 questions, so we'll go through those and continue on from there. Let me kind of make sure we're... There we go. Alright, so for the question here, we've got, which of the following is a property of a T network with series capacitors and a parallel shunt inductor? Is it A, low pass filter, B, band pass filter, C, high pass filter, or D, notch filter? So, while a T network is commonly used as an antenna tuner or transmatch, it can inadvertently become a high-pass filter under certain conditions, which is something you generally want to avoid in this application. Remember that capacitors decrease reactance with increasing frequency. Therefore, if these are in a series with the signal path, they will pass higher frequencies with less attenuation. Likewise, an inductor has more reactance with increasing frequency, which means if they are in shunt parallel with the signal path, they will bypass less of the signal at higher frequencies. If you use a high-pass T network as an antenna tuner, be sure your transmitter is clean, because the network will emphasize any harmonics you generate. So the correct answer is C. So which of the following is a property of a T network with series capacitors and a parallel shunt inductor? Correct answer is C, a high-pass filter. Okay, next question here, moving right along, folks. What advantage does a series L pi L network have over a series L pi network for impedance matching between the final amplifier of a vacuum tube transmitter and an antenna? Is it A, greater harmonic suppression, B, higher efficiency, C, does not require a capacitor, or D, greater transformation range. Ham sets transmitting into a multi-band antenna system can generate harmonics. The series L pi L network has a greater harmonic suppression. Correct answer is A. So what advantage does a series L pi L network have over a series L pi network for impedance matching between the final amplifier of a vacuum tube transmitter and an antenna? Correct answer is A greater harmonic suppression. All right. Which describes a pi L network used for matching a vacuum tube final amplifier to a 50 ohm unbalanced output? A phase inverter load network. B, a pi network with an additional series inductor on the output. C, a network with only 3 discrete parts. D, a matching network in which all components are isolated from ground. The pi L network is characterized by 2 series adjustable inductors and 2 variable shunt to ground capacitors. You can spot the pi L network over a simple pi network as the pi L network has an additional series inductor at the output. Correct answer is B. So which describes a pi L network used for matching a vacuum tube final amplifier to a 50 ohm unbalanced output? Correct answer is B, a pi network with an additional series inductor on the output. Don't we feel so educated? There is a lot to this test. I can't wait to get it done. All right, next question here. What is one advantage of a pi matching network over an L matching network consisting of a single inductor and a single capacitor? A, the Q of pi networks can be controlled. B, the L networks cannot perform impedance transformation. C, pi networks are more stable. Or D, pi networks provide balanced input and output. The big advantage of a pi matching network over the L network is the shunt to ground variable capacitors that can control the Q. Depending on the value of the variable capacitors and adjustment tap coil chosen. Correct answer is A. So what is one advantage of a pi matching network over an L matching network consisting of single inductor and a single capacitor? Correct answer is A. The Q of pi networks can be controlled. Now keep in mind on your exam, these may be in a different order for the answers, so that's one reason why I'm trying to make sure to read back over it again. Not saying they will be, but there's a chance it might. So, next question here. Which of the following describes how the loading and tuning capacitors are to be adjusted when tuning a vacuum tube RF power amplifier that employs a pi network output circuit? Is it A, the loading capacitor is set to maximum capacitance and the tuning capacitor is adjusted for minimum allowable plate current? B, the tuning capacitor is set to maximum capacitance and the loading capacitor is adjusted for minimum plate permissible current. Let me put this next page here. C, the loading capacitor is adjusted to the minimum plate current while alternately adjusting the tuning capacitor for maximum allowable plate current. Or D, the tuning capacitor is adjusted for the minimum plate current and the loading capacitor is adjusted for maximum permissible plate current. All right. If you're going to be running a big power amplifier on the HF bands, chances are it will still use a vacuum tube for kilowatts of output power. Solid-state power amplifiers require no tuning, but most solid-state power amps only put out about 800 watts maximum power. With a tube-powered amplifier, you alternately tune and increase the plate current with the loading capacitor, and then dip the plate current with the tuning capacitor. Do this for a short period of time, and do it on frequency that no one else is transmitting on. First tune up into a dummy load to get the settings close, then switch over to the antenna. Select a frequency that no one is using, announce I'm going to quickly tune up, and then do so quickly. Correct answer is D. So which of the following describes how the loading tuning capacitors are to be adjusted when tuning a vacuum tube RF power amplifier that employs a pi network output circuit? Correct answer D. The tuning capacitor is adjusted for maximum plate current, and the loading capacitor is adjusted for, the tuning capacitor is adjusted for minimum plate current, and the loading capacitor is adjusted for maximum permissible plate current. Sorry about that. Didn't want to make sure we had the terminology correct. Okay. Moving right along, folks. All right. How does an impedance matching circuit transform a complex impedance to resistive impedance? A. It introduces negative resistance to cancel the resistive part of impedance. B. It introduces transconductance to cancel the reactance part of impedance. C. It cancels the reactive part of the impedance and changes the resistive part to a desired value. Or D. Reactive currents are dissipated in matched resistances. Alright, so in older radios, you could vary the matching network to cancel the reactive X part of the impedance and change the value of the resistive part R of an impedance to the desired value. Newer transistorized radios have a fixed output and there is no manual control of the fixed matching device. However, manufacturers have come to the rescue in antenna matching by providing new radios with built-in automatic tuners. So the correct answer is C. So how does impedance matching circuit transform a complex impedance to a resistive impedance? C. It cancels the reactive part of the impedance and changes the resistive part to a desired value. All right, next one here. What causes intermodulation in an electric circuit? A. Too little gain. B. Lack of neutralization. C. Nonlinear circuits or devices. Or D. Positive feedback. Intermodulation interference is minimized by a careful selection of linear circuits and components. If that newly designed transceiver for 2 meters or for 40 megahertz that repaired repeater is experiencing high levels of intermodulation, the problem could be caused by non-linear circuits, devices, and components inside the receiver. The correct answer is C. So what causes intermodulation in an electric circuit? Correct answer is C. Non-linear circuits or devices. All right, last question on this page. What is the term for spurious signals generated by the combination of 2 or more signals in a non-linear device or circuit? A. Amplifier desensitization or desensitization. Yeah. Desensitization. Or B. Neutralization. C. Adjacent channel interference. Or D. Intermodulation. Repeaters are fun to operate through, but a real headache to keep on the air with a clean signal. The problem is intermodulation caused by other close proximity transmitters. What you may hear are two signals coming in at once. The resulting noise is commonly called intermod. So the correct answer is D. So what is the term for spurious signals generated by the combination of two or more signals in a nonlinear device or circuit? Correct answer is D, intermodulation. We should have probably guessed that one, given all the first couple of questions were all on that. All right, moving right along, folks. Keep that covered so we don't skip ahead. All right. How can intermodulation interference between two repeaters occur? A, when the repeaters are in close proximity and the signals cause feedback in the final amplifier of one or both transmitters. B, when the repeaters are in close proximity and the signals mix in the final amplifier at one or both transmitters. Or C, when the signals from the transmitter are reflected out of phase from airplanes passing overhead. Or D, when the signals from the transmitter are reflected in phase from airplanes passing overhead. I'm thinking A. All right, intermod, in its true sense, occurs within the repeater's final amplifier. When signals mix in one or both repeater amplifiers, sum and difference signals, you want to make sure that's nice and clear, are heard on many different frequencies and as significant noise on the frequency of the repeaters. Correct answer is B. So I guessed wrong. How can intermodulation interference between two repeaters occur? Correct answer is B. When the repeaters are in close proximity and the signals mix in the final amplifier of one or both transmitters. Okay. What are we doing on time? Not bad. And then you can kind of see here a little picture of a communications tower array. And it talks about repeater sites like this one require hams to use added cavities, circulators, filters, and high-end duplexers to minimize intermodulation interference. And it kind of shows basically a series of like two or more tower arrays with multiple different signals coming off. One looks like a cell phone tower, so on, and there's power lines nearby. Is what the picture looks like. There, take the bright off from it and you can see it a little better. All right. So, moving right along, next question here. So, which of the following filters would be the best choice for use in a 2-meter band repeater duplexer? A crystal filter. B, a cavity filter. C, a DSP filter. Or D, an LC filter. Okay. Well, up in the question before, it talked about a cavity, but let's make sure. For a 2-meter repeater duplexer system, we need big filters. We call them cavity filters because they are hollowed out to form extremely narrow band tuned resonant circuits. So the correct answer is B. Which of the following filters would be the best choice for use in a 2-meter band repeater duplexer? Correct answer is B, a cavity filter. And it goes on showing, actually looks like hot water tanks. It says, the professional cavity filter system on a 2-meter repeater offers minimal attenuation to receive signals in the passband and major attenuation to the repeater's transmitted frequency. It is a job to filter out your transmit signals only 600 kilohertz away. Make sure these filter cavities are in a dry, warm cabinet to prevent condensation on the gleaming copper's insides. Okay. They look like hot water tanks in the picture, but those are actually your cavity filters. And I've seen some videos out there, people building repeaters where it shows almost like several of these on a rack along with everything else for the repeater. Okay, next question here. Which of the following may reduce or eliminate intermodulation interference in a repeater caused by another transmitter operating in close proximity? A bandpass filter in the feed line between the transmitter and receiver. B, a properly terminated circulator at the output of the repeater's transmitter. C, utilizing a Class C final amplifier. Or D, utilizing a Class D final amplifier. Your ham friends who regularly trek to mountaintops to maintain ham radio, VHF, UHF repeaters deserve your major support. Mountaintop repeaters are located in the worst RF environments possible, in the midst of hundreds of nearby signals that may desensitize the receiver or create garbage on the input. Everything was fine when your team left the hill, but a new land mobile radio system on the same tower is now causing intermodulation interference. One solution is to install a terminated circulator or ferrite isolator between your own transmitter and duplexer, which helps zero in your own frequency and cancel out any other off-channel frequencies that seem to creep in only when your equipment is on transmit. So the correct answer is B. So which of the following may reduce or eliminate intermodulation interference in a repeater caused by another transmitter operating in close proximity? Correct answer B, a properly terminated circulator at the output of the repeater's transmitter. And looks like last and final question of this chapter before we move on to amps and power supplies. So the last question here: what current flows equally on all conductors of an unshielded multi-conductor cable? A differential mode current. B, a common mode current. C, a reactive current only. Or D, a return current. Common mode currents are just what they sound like, currents that are equal in amplitude and phase on two or more conductors. The best way to reduce common mode currents is to use common mode choke, such as passing the entire bundle through a single toroidal ferrite core or a string of ferrite beads. Correct answer is B. So what current flows equally on all conductors of an unshielded multi-conductor cable? Correct answer is B, common mode current. And it kind of shows here are some web addresses of useful sites related to modulate your transmitters. There's www.dx-code.org, www.qrz.com, www.hamcall.net/call, and www.dxzone.com/catalog/dx_resources/call signs. And that finishes up that chapter. And again, the next video we do will start on amps and power supplies. Check that out. All right. So with that, we'll close this out. Well, I appreciate everybody stopping in and studying along with me. And I'll continue to do this. I will still try to do some off and on in live videos as well. A couple of them that I've done, I kind of like how it goes along. Some of the ones popping in and joining in with me, trying to answer some of the questions too, becomes a little more interactive. I appreciate that. So with that, guys, I'll say happy studying. Get on the air. 7-3.